Okay, so today we're gonna like dive into something pretty cool. It's all about, how to make AI like way better at medical reasoning.
Absolutely.
And for you guys listening, like if you want to like get up to speed on this stuff fast without like,
Yeah.
drowning in the technical details, this is like the perfect episode for you.
Yeah, this is going to be a good one.
It's basically like we're giving you the cheat sheet to this
Mm-hmm.
super cutting edge approach in medical AI.
For sure.
Right.
Right.
Yeah.
So today's deep dive is all about
Yeah.
a new technique
Okay.
called test time scaling
Test time scaling.
and how researchers are using it
Okay.
to like seriously boost the reasoning skills
Right.
of large language models in medicine.
Yeah.
So our roadmap for this journey is a research paper.
Okay.
It's called Unleash the Potential of Test Time Scaling for Medical Reasoning with Large Language Models.
Yeah. And the main idea behind test time scaling is like surprisingly simple.
Right.
It's all about giving these AI models like more space to think when they're trying to,
Yeah.
figure out these complex medical questions.
Exactly.
So the researchers, they developed a specific method.
Yeah.
They're calling it M1.
Mm-hmm.
And we're going to break down, exactly how it works and like
Yes.
what it means for the future.
Okay, so let's kick things off by understanding this whole concept of
Okay.
test time scaling.
Okay.
At its core, it's basically about giving an LLM
Okay.
more computational resources during the inference stage.
Right.
So that's the point when it's actually trying to generate an answer.
Yeah.
Specifically, it means increasing what we call the thinking token budget.
So like for our listeners who are really like, want to understand this thoroughly,
Right.
it's like if you give it more thinking power, it should like in theory lead to better answers.
Yeah, more accurate and well-reasoned answers.
Especially with like,
Especially when we're dealing with all the complexities of like medical knowledge and all the decisions that have to be made.
Yeah, totally.
Precisely.
Yeah.
Now, the inspiration for all of this
Okay.
actually comes from some pretty impressive successes in other fields,
Okay.
particularly in math.
Oh, interesting.
You might have heard of OpenAI's O1
Mm-hmm.
or the open source S1 method.
Yeah.
These approaches showed that letting AI models like run for longer,
Okay.
letting them process more information when they're reasoning
Mm-hmm.
could lead to like huge improvements in solving these really tough problems.
So it's almost like letting them think longer on it.
Yeah, basically.
Yeah.
But here's where it gets really interesting.
Okay.
Applying this to medicine isn't quite as simple.
Okay.
It's not just a copy-paste.
Right.
Medical knowledge is so vast and nuanced.
Yeah. It's a whole different ball game.
Yeah, way more complex.
It's complex biological systems.
Yeah,
And of course, the stakes are super high.
yeah, absolutely.
We can't have AI systems making like harmful recommendations.
No, definitely not. So this raises a big question for our deep dive today.
Okay.
Can a technique that worked so well
Right.
in the logical world of math
Mm-hmm.
actually translate to the more intricate and knowledge-heavy world of medical reasoning?
It's a good question.
That's the main thing this research is trying to figure out.
Okay.
So,
Yeah. So tell me a little bit more about M1. Like, how does it actually like,
yeah.
boost this thinking process for medical questions?
So M1 is presented as like this lightweight but powerful method
Okay.
for using test time scaling,
Mm-hmm.
specifically for medical question answering.
Right.
The researchers had a really systematic approach to developing it.
Okay.
They broke it down into 3 main stages.
Okay. So let's go through those stages. Like,
Yeah.
what was the first one?
All right, so the first crucial step was data curation.
Okay.
They started with a massive data set, something like 196,000
Wow. That's a lot.
medical question answer pairs. This data came from a bunch of different public data sets,
Right.
including MedMCQA, MedQA USMLE, HeadQA, and PubMedQA.
Oh, wow. So they really like pulled from all over the place.
Yeah, they did.
Okay. But I imagine like the quality and difficulty
yeah.
of all those questions was probably pretty different, right?
Absolutely.
Yeah.
So the next step was super important.
Okay.
It's what they call difficulty filtering,
Difficulty filter.
to really focus on the questions that needed deeper reasoning.
Mm-hmm.
They used pretty advanced LLMs themselves.
Okay.
They used Qwen 2.5 models
Mm-hmm.
with 7 billion and 32 billion parameters
Okay.
to try and answer those initial questions.
Right.
Now, if either of these models could get the answer right,
Mm-hmm.
they actually filtered that question out.
Oh, interesting.
The idea there was they wanted to train their new model
Okay.
on the really hard medical problems.
Right.
the ones that even smart AI struggled with.
Oh, so they're like
Yeah.
really trying to isolate the tough ones.
Exactly. This whole process narrowed down the data set to about 37,000 of the toughest questions.
Okay, so they're really getting to the nitty-gritty.
Yeah, exactly.
Okay, so what was next?
All right, so next up was what they call thinking generation.
Thinking generation.
So for those 37,000 tough questions,
Yeah.
they used an even more powerful LLM
Okay.
called DeepSeek R1.
DeepSeek R1.
This one was used to actually generate detailed explanations,
Okay.
step by step, leading to the right answer.
Right.
They then really carefully checked those solutions to make sure DeepSeek R1's final answer matched the actual correct answer.
Right.
This whole process gave them about 23,000
Wow.
high-quality thinking answers pairs.
Okay, so now they've got this like awesome curated data set
Exactly.
of hard medical questions with like these verified in-depth answers.
Verified and explained.
It seems like that would be like super valuable data for training.
Oh, yeah, definitely.
Okay.
But they went a step further.
Oh, they did.
They did some diversity sampling.
Diversity sampling.
They wanted to make a smaller, more representative training set.
Okay.
They took into account medical specialties
Okay.
using something called MESH categories.
Okay.
Those are like standard classifications for medical topics.
Right.
They wanted to make sure they had a good mix across all areas of medicine.
Makes sense.
They also looked at which original data sets the quotients came from
Okay.
to keep things balanced.
Okay.
This careful sampling resulted in a super high-quality subset of 1,000 examples,
Okay.
which they called M1K.
M1K.
The other 23,000 examples formed another data set called M23K.
M23K. So.
All right, so now they've got these super curated data sets.
Yeah.
What did they do with them?
All right, so that's where the actual model training comes in.
Yeah.
This was the second key step in developing M1.
Okay.
They took the base Quen 2.5 models, both the 7 billion and 32 billion parameter instruct versions,
Okay.
and they fine-tuned them.
Using supervised fine-tuning, SFT for short,
SFT.
on those curated M1K and M23K data sets.
Right, and this training process is what
Yeah.
created the different M1 models we've been hearing about, right?
Exactly.
Okay.
So they made three main variants
Okay.
of the M1 model.
Okay.
First, you've got M17B1K,
Okay.
which was trained using the 7 billion parameter model on the smaller 1,000 example M1K dataset.
All right.
Then there's M17B23K,
Okay.
which used the same 7 billion parameter base model, but was trained on the bigger 23,000 example M23K dataset.
Okay.
And lastly, there's M132B1K,
Okay.
which uses the more powerful 32 billion parameter base model trained on the smaller M1K dataset.
So they're basically playing around with both the size of the AI model and how much of that high-quality reasoning data it learns from.
Right.
And the training format was like question, then reasoning, then answer.
Yeah.
They were specifically teaching it to think step by step.
Exactly. That format is designed to teach the model
Yeah.
to think through the problem before jumping to the answer.
Makes sense.
Yeah.
All right, so we've covered how they got the data and trained these models.
Yep.
Now, how does all this thinking more actually work when the model's answering a new medical question?
Right. So that's the inference stage.
Right.
When the M1 model is given a medical question it's never seen before, the researchers can control how much it thinks
Okay.
by setting something called a thinking budget.
A thinking budget.
This budget is basically the maximum number of tokens.
Okay.
Remember, tokens are like the building blocks of language.
Yeah, like words or parts of words.
Exactly. That the model's allowed to use in its reasoning process before it gives the final answer.
Right.
So a bigger thinking budget means the model can come up with a longer, more detailed chain of thought.
Okay. So they're basically limiting its thinking power.
In a way, yeah.
Okay. And there was also this weight token technique?
Yes.
That they were using.
Yeah, the weight token technique.
Yeah.
This is how they did what they call budget forcing.
Budget forcing.
So if the model finishes its reasoning before it's used up its entire budget, they can basically tell it to wait and keep thinking.
Oh, interesting.
The idea is to encourage the model to double check.
Okay.
Maybe look at other ways to solve the problem or explain its thoughts more.
Right.
This actually worked really well in math.
Oh, okay.
So they wanted to try it here.
Gotcha. So they're giving the AI like a certain amount of thinking tokens and even a way to make it keep thinking if it's like, finished early.
Exactly.
So what happened when they tested it out?
So the results are really interesting.
Yeah.
First of all, the main idea of test time scaling was confirmed.
Okay.
They saw that accuracy improved on a bunch of different medical benchmarks as they increased the thinking budget. Yeah. Figure 1 in their paper shows this really clearly.
Okay.
Performance goes up for the different M1 models.
Makes sense.
And the data sets they tested them on.
Yeah. More thinking power should lead to better results.
Right.
But I remember there was a catch.
Yeah, there's a key finding.
Like there was an optimal point for thinking.
Yeah. They found that there's actually an optimal reasoning token budget.
Okay.
It's around 4,000 tokens.
Interesting.
If they let the models go beyond that,
yeah,
their performance sometimes actually started to drop.
Oh, wow. So too much thinking is bad.
It seems that way.
Okay.
They think this might be because of overthinking.
Okay.
The model might get distracted by unimportant details.
Right.
Or start second-guessing itself.
Interesting.
So the key takeaway here is that more thinking isn't always better.
Yeah, there's a sweet spot.
Exactly. Now, what about that weight token technique?
Yeah, what about that?
The way of making the model keep thinking,
right,
even when it thinks it's done.
Yeah. Did that help with medical question answering?
So this is where things got different from the math world.
Okay.
In medical QA, forcing more reasoning with the weight tokens didn't always improve things.
Okay.
Sometimes it even made things worse.
Really?
Yeah, they show this in Figure 3 and Figure 5.
Wow, so it actually made previously correct answers wrong.
Yeah, it did.
That's so weird.
It is kind of counterintuitive.
Yeah, why would that happen in medicine specifically?
They think this might be because sometimes the models don't have complete medical knowledge.
Okay.
So when they're forced to think more, they might grab onto a wrong piece of information.
Right, and change a right answer to a wrong one.
Exactly.
So it's really different from math then.
Yeah, it highlights a key difference.
Like in math, more thinking usually helps.
Yeah.
But in medicine, if the model's knowledge is flawed, more thinking might just make it worse.
Yeah, it could lead them down the wrong path.
That's fascinating.
It is.
Okay, so what else did they find?
So another really important finding is that the main obstacle in medical AI reasoning often isn't the thinking time. It's the model's medical knowledge.
So the knowledge itself is the bottleneck.
Exactly.
Okay.
You can see this in Figure 4 and Appendix Figure 7.
Okay.
A model might do a ton of reasoning, but still get the wrong answer if it's missing a key piece of information.
Right.
For example, the M17B1K model didn't know that the anterior ethmoidal artery belongs to the internal carotid.
Okay.
And that messed up its reasoning, even though it had a big thinking budget.
Right.
Whereas the M17B23K and M132B1K models, they did have that knowledge.
Okay.
And could reason better.
So it's not just about thinking more.
Right.
It's about having the right knowledge.
You got it.
Okay.
The researchers found that increasing the amount of training data and using bigger base models were more effective at dealing with this knowledge problem.
So better data leads to better knowledge. Exactly. Which then lets the test time scaling work better.
Precisely.
Okay.
You can see this in Table 2.
Okay.
Where the filtering and sampling they did really helped.
Makes sense.
Now, despite the fact that M1 is pretty lightweight and the training data sets were smaller compared to other medical LLMs, the M1 models actually did really well.
Oh, wow. That's great.
On these medical benchmarks.
Okay.
For instance, M17B23K hit a new state-of-the-art accuracy of 60.32%.
Wow.
That's among models of its size.
Okay.
And it even beat Huachu GPT-017B.
Huachu GPT-017B.
That model uses a much more computationally intensive approach with reinforcement learning on a bigger data set.
So M1 is more efficient?
Yeah, way more efficient.
That's amazing.
It is.
Okay, so test time scaling really works.
It does.
When you combine it with the right data and a good model.
Exactly.
What about the bigger M132B1K model?
Yeah, so M132B1K actually performed as well as much larger medical LLMs.
Oh, wow.
Ones with 70 billion parameters or more.
Wow. Okay.
You see this in Table 1.
Table 1.
This really shows how efficient test time scaling can be.
Yeah, it's pretty amazing.
So,
yeah, it really highlights that difference between medical and mathematical reasoning. Medical reasoning seems way more reliant on having that accurate knowledge.
Right.
It's not just about like raw thinking power.
Exactly.
Yeah.
In math, a model can kind of figure things out, even with limited knowledge.
Okay.
But in medicine, if you're missing a key fact, it can completely derail your reasoning.
No matter how much you think about it.
Exactly.
Okay, and they also talked about a specific failure case, right?
Yeah, so in Figure 7 and in Appendix C.
Okay.
They show an example where the model actually got the right answer at first with good reasoning. But then when they made it keep thinking, it went and grabbed some wrong anatomical information and changed its answer to a wrong one.
So more thinking actually hurt it in that case.
Yeah, it did.
Okay, so to sum it all up for our listener, what's like the most important takeaway from all of this?
Okay, so the main message here is that test time scaling is a really promising technique. It can help AI reason better in medicine.
Okay.
By giving these models more time to think, we can actually improve their accuracy.
That's great.
But there's a big caveat.
Okay.
It only works if the model has good medical knowledge.
Right. So the knowledge is key.
Exactly.
Yeah.
Simply giving an AI more time to think isn't enough.
Right.
It needs a solid foundation of accurate information.
Okay.
And the M1 research shows a really efficient way to do this. It got amazing results with smaller data sets than some other top medical LLMs.
Yeah. Yeah, it really shows how important it is to optimize the thinking process itself. And for anyone who wants to explore this further, they've made their data in code public.
They have?
Which is awesome.
Yeah, it's a fantastic resource.
So like stepping back a bit, it's kind of crazy that even advanced AI can overthink.
It is interesting.
It's still limited by what it knows.
Yeah.
What does that mean for the future of AI in medicine?
Right. It really makes you think.
Yeah.
It seems like progress won't just come from making models bigger and bigger.
Okay.
It's also about giving them the best possible knowledge.
Right. Like super high quality information.
Yeah, exactly.
It's not just about brute force computing.
Nope.
Yeah.
It's also about how we represent medical knowledge itself.
It's a really cool area of research.
It is.
Lots of challenges and opportunities ahead.
Yeah, definitely.
Okay, well, thanks for breaking all that down.
No problem.
That was a really interesting deep dive into M1.
Yeah, I'm glad you enjoyed it.
And for everyone listening, be sure to check out the show notes.
Yes.
For links to the paper and all the other resources.
All the details there.
And as always, thanks for tuning in to The Deep Dive.
Thanks, everyone.
We'll catch you in the next episode.
See you later.